or antimicrobial resistance in aquaculture. Sorry, I have to. Which button?
Right button. The right button.
Okay. So just to start my presentation, so aquatic animal diseases is still considered as a major bottleneck in the sustainability of aquaculture in the Asia-Pacific region. So these diseases includes important, so those that are having, bringing havoc to the aquaculture industry for a long time, as well as emerging diseases, which we have maybe one emerging diseases every few years. So the spread of these transboundary aquatic animal diseases is directly correlated to the transboundary movement of live aquatic animals and aquatic animal products. And these diseases are the main reason why we are using antimicrobials in aquaculture. So AMR in aquaculture is a significant global challenge, especially at present, where important bacterial pathogens develop resistance to antibiotics or antimicrobials, and therefore posing threats not only to the aquatic animals, to the cultured aquatic animals, but also to human health and the environment. So this is driven by the widespread, often prophylactic use, or those that are used for disease prevention, and misuse of antimicrobials that creates a selective environment for resistant bacteria to thrive and share resistance genes. So AMR is emerging as a systemic risk to aquaculture, threatening not only the aquatic animal health and productivity, but also food safety. I think Dr. Nui mentioned this a while ago. Trade, environmental integrity, and human health under the One Health approach. So in terms of farm production, so AMR or antimicrobial resistance can result to higher cost because of increased use of antimicrobials, lower survival because of the frequency of disease outbreaks, and failed treatments. When we have resistant strains of pathogens, then they will not respond to any treatment. So it has effect on public health, the transfer of resistant genes from aquatic animal pathogen to human pathogens. So the aquatic environments, we have a lot of human pathogens that are thriving in that environment. And this, if we continuously use antimicrobials or antibiotics, it can develop these resistant strains of aquatic animal pathogens wherein the genes can be transferred to the human pathogens. And of course, it has an effect in market and trade. There will be export restrictions or rejections of shipments due to antibiotic residues, and of course, the food safety issue. So consumers now are more concerned on the safety of the products that they are consuming. And for food security, this is a long-term risk to sustainability of aquaculture. So what are some of the alternatives to antimicrobials that we have now? So we have one that are already established or that are already being used at the farm level. So this include vaccines, immunostimulants and phytochemicals, probiotics, prebiotics, and symbiotics, and some systemic enclosures and ecological management. So this is more on the pond management. For example, the use of biofloc technology, the recirculating aquaculture system, and improved biosecurity. So these are all preventive measures to avoid the occurrence of diseases during the culture of our important aquatic animal species. But we also have emerging technologies and the next generation therapeutics. So this includes the DNA and RNA particle vaccine. We have the quorum quenching. This is inhibiting the quorum sensing ability of most bacterial pathogens. So mostly the pathogenicity of the bacteria can be enhanced through their quorum sensing. That is how microbes communicate with each other. So if we will stop this, if we will quench this quorum sensing of the bacteria, then we can prevent this bacteria to become pathogenic and more problematic. So we also have antimicrobial peptides and bacteriocins, bacteriophages, very promising, postbiotics and parabiotics. So these are just probiotics, but the postbiotics are killed cells of beneficial microorganisms, and parabiotics are the inactivated cells of beneficial microbes. And of course, we have the nanobubble technology, which are now being used by some farmers for water quality management and later for vaccine delivery, and also the genomic selection and selective breeding. So the production of specific pathogen-free, resistant, and tolerant strains, and of course the potential of genome editing for the production of resistant strains of important aquaculture species. So let us look at these different ATAs in terms of their evidence on effectiveness, the policy, and of course how the technology readiness of this. So these are the different vaccines that have been developed or are being developed. We have inactivated vaccines. It is already shown very effective, especially in the salmon industry in Norway. So, and there's a clarity policy-wise, it's high, and the technology is already there. So there have been commercially available vaccines that can be used for some of important aquaculture species. Then we have the DNA vaccines and recombinant vaccines. They are very strong in effectiveness, especially under the laboratory. Policy clarity is moderate or a bit complex in some, especially in countries here in the Asia-Pacific region. And technology readiness is already high. So we have, next is the probiotics, prebiotics. Effectiveness is moderate because it depends on what kind of probiotics you are using in your farm and how your cultured organism is responding. So policy clarity is a bit low, so we don't know if can be considered as a feed additive, so which pathway of registration will it go, but the technology readiness is already there, medium to high. Phages, bacteriophages, this is very effective, very specific to a particular pathogen, but it still requires field validation. Very low policy clarity because, again, we don't know if this is a treatment method, a feed additive, a probiotic. So the registration of these products, bacteriophages products, still a big question mark in many countries, especially for the aquaculture industry. And the technology is somehow a bit ready at a low to medium. And quorum quenching, some can be specific, but the policy clarity is still low, and the technology readiness is low to medium. So we have postbiotics and parabiotics, antimicrobial peptide, which has very moderate effectiveness and low policy clarity and low to medium technology readiness. The nanobubble technology, that's why I told you this is already being applied at the farm level, mainly for water quality management, for water disinfection, and its evidence for effectiveness is very, very strong. Policy clarity is moderate because these are more on a pond management side that they are being implemented or adopted by the farmers, and technology readiness is medium to high. So, but this technology is also now being explored for vaccine delivery, that is the nano vaccine. But again, if you mention vaccine, you will go to the first one, the regulatory barriers in using vaccine at the farm level. Selective breeding for disease tolerance and resistance is a very strong, and policy clarity is clear because there's not much. If you develop a good strain, then you can just introduce it. But the one I will point out here is the genome editing, which is now being applied in many countries for developing strains that are resistant to diseases or that can tolerate extreme conditions. And the positive side of this is they are not considered as GMO or genetically modified organism because you are not introducing any foreign gene into the organism, so you are just editing what is existing in that organism. So blocking some genes to prevent them to, consume more energy for reproduction, things like that. So fast growth, higher tolerance to salinity or temperature, and of course, the more important is disease resistance. And of course, biosecurity, we need this for disease prevention. But this is easier said than done because especially for small-scale farms where biosecurity is a bit restrictive because of their limited capacity to employ basic biosecurity practices at the farm level. So we have a lot of these innovations and technology, but what are these barriers that are preventing them for the farmers to adopt this technology? So some of these are regulatory barriers, that's what I mentioned. So there is a very unclear, in most countries, not only in Thailand, but in most countries in the Asia Pacific, there are unclear or fragmented regulatory frameworks that delay the approval and commercialization of these products. So as I mentioned, vaccines, so we have very, very limited vaccines for use here in the region, Asia Pacific region. Yes, they will say the salmon industry in Norway, but as we know, salmon is high-value fish, wherein in the Asia Pacific region, we are culturing mostly low-value fish. So that is also one of the reasons why we cannot adopt vaccine. For developing vaccine is very expensive. It will add to additional cost of production, and it might not be, practical to use it for low-value fish. So market and economic barriers, okay, this one. So again, these ATAs will entail additional cost in the overall production. So if the additional cost will not justify, the production, the profit that will be incurred in producing the fish or shrimps, then the farmers will not take it. So ATAs may require upfront investment, but the result is not yet, guaranteed. So there will be hesitations among farmers to adopt it. So knowledge and behavioral barriers, so limited extension services, weak advisory systems, and low trust in new products that will hinder adoption. And also, I will add here is the awareness of the farmers, because sometimes you develop the technology, but how you will explain it to the farmers at their language, because farmers want results, they want to see, so they will not believe you if they will not see the result. So explaining them the mechanism on how this product will help them in preventing diseases is quite a challenge, especially for the innovators like us. And last is the delivery system constraints. Of course, you have the input supply chains for ATAs are often underdeveloped. Sometimes we need cold storage, for example, for vaccines, for bacteriophages. You cannot just transport them to the remote areas in the farms without these cold storage facilities. So those are the things that will hinder the dissemination or distribution of these ATAs, especially in rural and smallholder contexts. So to end, the transition to alternatives to antimicrobials in aquaculture is both urgent and achievable. So we have the technology, we know we have proven them effective, but we have this last mile gap that we have to traverse in order to bring this technology down to the farmers. So the technologies and approaches required to reduce antimicrobial dependence already exist, but the challenge lies in aligning the policy, market, delivery systems to enable their adoption at a scale or at the farm level. So it is recommended that a roadmap is needed to provide a structured pathway for moving from fragmented innovation to coordinated system-wide transformation, positioning aquaculture as a part of the solution to AMR rather than a contributor to the problem. So we have a lot of work to do. We have all the innovations, we have all the technologies that are proven effective as alternatives to antimicrobial. In aquaculture, all we need to do is to bring these products to the farmers. So that's the challenge for all of us. I have to stop here. Thank you very much.
Thank you, Dr. Ed, for sharing with us the emerging technologies and therapeutics, and more importantly, what's holding us behind right now from using this technology สำหรับวิทยากรท่านถัดไปนะคะขอสวิตช์กลับมาเป็นภาษาไทยนะคะเราได้รับเกียรติจากรองศาสตราจารย์ดร.วรพลชัยกิรติศักดิ์จากคณะวิทยาศาสตร์จุฬาลงกรณ์มหาวิทยาลัยนะคะ